All right, so today we are going to look at chapter 5, which is on probabilities, okay? And it's a necessary chapter, but it often turns out to be people's least favorite chapters, okay? So, I know, right? I hope you have a favorite chapter so far, because this one's probably going to be your least favorite one. But it's not too bad. It's just it's something we do have to learn, okay? And the reason for this is we need to understand probability so that when we look at data in the future, there is a context in which we can understand it, okay? So for example, if you were an alien from another planet and you came to Earth and you saw the first person you met, or the first creature you met was LeBron James, okay? You would have no idea, because there's no this is your first time looking at this, or you have no context, and you would have no idea that LeBron James is a tall person, or that he's a good basketball player, or things like that, okay? You would have no context, okay? Only after, studying and understanding a little bit about people would you understand, oh, you know what? Most people are between 5 feet and 6 feet tall, or maybe 6'2" or something, okay? And LeBron, he's really tall compared to most other people, and so that would give you some context. But until you understand a little bit about the context, and in this case, this is kind of what probability kind of serves as this background information on data that we're going to look at, okay? But because of the way, there's all these like rules that you have to learn about probability, sometimes it's very easy to get lost in the rules. It's very easy to say like, oh, I gotta learn this rule and remember this rule and this rule, and it's easy to forget that the reason why we study probability is to form this background on in terms of the future data that we see. Okay, so that's the reason why. But yeah, I do have to teach you the rules regarding probability, and it's easy to get lost, right? I guess it's kind of like maybe you're trying to you're trying to get a foreigner or someone to enjoy the game of basketball or something, and so I mean, the best way is just to say, hey, watch the game, and if you have questions, ask along the way, okay? But here we're kind of we don't have that luxury. I can't sit alongside of you and kind of go along and we're going to look at data together and have a happy jolly time. Okay, I've got to explain all of the rules of probability in this 3-hour session, so now it's like, okay, now I'm trying to explain basketball to you, and I'm going to be like, oh, okay, there's 5 players on each team on the court at any time, and they're allowed to, if they want to move the basketball, they have to keep it bouncing on the ground. They can't hold it and walk and up to 3 steps. Or it's going to feel like, oh man, you're explaining all these rules, and it's easy to get lost, right? If you're trying to understand a sport, it's easy to just get lost in all the technical rules, and it's going to feel like I'm explaining a lot of technical rules, because you do have to understand that. But again, this is to help us understand whether something is likely to happen or unlikely to happen, and what are the rules that determine whether something is likely to happen or unlikely to happen. And that's the background, much like in basketball. It's really, you just want to get the ball into the hoop, but there are rules and things that go into it, and it's easy to get lost. So I don't want you to get lost in the rules, even though you do have to know the rules. So I don't know what else I can say. But, let me just close this door. Okay, did everyone turn in their homework and pick up their graded stuff? Okay, well I hope so. If you haven't, you can pick up your graded stuff during the break. but we're going to get started. Okay, so here we go on probability. Okay, and so probability, we use probability to understand how likely or unlikely an event is. Okay. And to kind of understand how likely or unlikely something is, we have to understand something about randomness, okay? So random is one of those words in English that has now been abused and has lost much of its meaning. And as a statistician who associates a certain meaning to random and randomness, it crushes my soul to hear to see people write LOL random and LOL so random. No, that's just maybe odd. Okay, so that's so random is used to explain something. There's all sorts of meanings we can associate with this, but maybe a random event is an event where the outcome is unpredictable. But just because something is unpredictable doesn't mean we can't understand it. So, for example, if I take a coin and I were to flip it, okay, you would not be able to predict with 100% accuracy what the result of this coin flip is going to be, okay? You can just guess. You can say, I'm going to guess that it's going to land heads, or I'm going to guess that it's going to land tails, okay? So you can't predict the outcome of a coin flip. However, we can understand something about coin flips. We know that if I were to flip the coin 100 times, about how many heads should I see? About 50, right? And if I see 52 heads, that's fine, right? If I see 47 heads, also fine, okay? But if I flip a coin 100 times, and it lands heads 4 times, then you'd say something's not quite right. You're either flipping the coin in a weird way, or your coin is unfair, or you don't know the difference between heads and tails or something. Okay, if you flip a coin 100 times and I'm telling you, yesterday I flipped the coin 100 times and it landed heads 4 times, you're going to say, I think you did something wrong. Okay, so there's something we understand about coin flips, even though anytime we look at an individual coin flip, we have no idea what it's gonna, how it's gonna land. Okay. So, example. cannot predict the outcome of an individual coin flips. Okay? I guess I should write coin flips are random events. But we can understand something about flips, something. Here I'm writing, if I flip a coin 100 times, I expect it to land heads about 50 times. Okay? If it lands heads, say 47 times, okay, no big deal. However, if I flip a coin 100 times and it lands heads 4 times, we will be suspicious. Suspicious, alright? So, is everyone okay with that? Now, why are we suspicious of the coin landing heads only 4 times?
It's unusual.
Because it's unusual, okay? In our brain, we understand that the probability of this event, flipping a coin 100 times and it landing heads only 4 times out of 100, is very unusual. We understand that the likelihood or the probability of that happening is very low. Okay? On the other hand, flipping a coin 100 times and it landing heads 47 times is not unusual. We see somewhere in our brain we're saying, that's quite probable. Okay? So we'll say, high probability, low probability. And that's why we are suspicious. We don't know exactly what's going on, but we're thinking, you know what? You're either going to say, I don't think this actually happened, or I think something is wrong with your coins or your flipping method or something. Okay? And that's basically what we're trying to aim at with probability. Okay? We want to understand, you know, why is this one unlikely and why is this likely? Okay? So that's kind of where we're heading. So let's take like a little detour and let's talk about you know, one of the tools that we can use to understand probability is random numbers. Okay, so Okay, random digits, random numbers, they're pretty much the same thing. Alright? So basically, a random digit is, we go to a computer or some system. So I take a die that has 10 sides to it, and the sides say 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Okay? So one of the 10 digits, and basically I'm going to roll it, and whatever digit shows up, that's my random digit. Or I put 0 through 9 on slips of paper, I put them in a hat, I mix up the hat, and I pull out a digit. Okay? You know, there's something to that degree. Okay? So each digit, 0 to 9, has an equal chance of a parent. Alright? And we can use a physical method like rolling a die or drawing slips out of a hat. Okay? So digits can be generated from a physical method. Or we can use a computer. Okay? Computer and or a random digits table with a computer or a random number table. Okay. And again, random digits in of itself is not probability, but it helps us to understand some probability of some events happening. Okay. So these digits. Probability of events. Okay. So in our brain, so a very simple example that we understand. We already understand how a coin flip works. We understand that if you flip a coin a whole bunch of times, about half the time it should land heads, and about half the time it should land tails. Okay? We understand how that works. But what if I said, you are going to flip a coin and roll a die, and I want you to tell me how often it's going to land heads and give you an even number, or something like that. Okay? And we can, I mean, there's rules in probability. We're going to learn some of these rules where you can solve the answer directly. Okay? But sometimes there's these complicated situations, and that's not too complicated in all honesty. There's complicated situations that are, it's really hard to apply all of the rules, okay? Because, so, you know, we haven't learned the rules yet, but a lot of times you can solve them using the rules, and the other way is you can say, man, the rules get too complicated, the math work gets too complicated, so I'm just going to simulate what's going to happen. Okay, and we do simulations with random digits. Okay, and that's kind of how like traffic. Believe it or not, LA DOT and Caltrans, they try to simulate traffic on the freeways. And you're like, there's always traffic on the freeways, but they're trying to figure out things, and they're trying to figure out, when's the best time to do construction on the freeway so it doesn't ruin everyone's life. Yeah, I know, it's still gonna ruin your life, but, well, not really, but just delay or inconvenience your life, okay? But they're, they try to figure out these things, and they apply simulations. They're trying to figure out, what's the best timing rate on the, the meter that lets you onto the freeway? Should I just let it be green the whole time, or, should I stop red for every, they try to figure these things out, and they do them with simulations, okay? And at the heart of every simulation, we're not gonna do complicated simulations like that, but at the heart of every simulation is a random digit, okay? Are random digits, and we use these things to simulate random events, okay? So again, with random digits, the digits 0 through 9 have an equal chance of appearing, okay? And so if I wanted, in the most basic example, if I wanted to simulate a coin flip, okay? So we have to think of what the real life looks like. So in real life, heads has an equal chance of showing up as tails, right? Shows up as often as tails. So how can I simulate this using random digits, okay? Well, what we're going to do is we're going to somehow look at the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? These are the digits that could appear, and when they show up randomly, maybe I will see a 7, and then a 1, and a 0, and a 0, and a 9, and a 5, okay? And so these are just digits that show up maybe randomly. Somehow I want to use these digits to simulate a coin flip, okay? So to do this, I need to simulate it properly, I just need to make sure that this real life thing holds true. So I can say, with the random digits, I want to make sure heads shows up as often as tails, so I could assign to heads digits 0, 1, 2, 3, and 4, and assign to tails 5, 6, 7, 8, 9. Okay? And therefore, each of these digits have an equal chance of showing up. I've got 5 of them assigned to heads, and I've got 5 of them assigned to tails. So heads and tails, in the long run, will show up in about the same number of times. Is that good? Yes?
Why are you assigning half of the numbers to heads and half the numbers to tails? I mean, I know you said that, but maybe it's not.
Okay, so somehow, so when I ask a computer, simulate coin flips, okay, it doesn't have coins inside the little box, and it's not going to be sitting in the corner flipping coins, okay? It just, all it can do is say, all right, here's a random number, 3. Here's another random number, 2. Here's another random number, 1, okay? Okay, that's not really random. I was pulling those out of my head, and I'm not a computer. But a computer does a much better job at doing random numbers. So you're going to say, okay, it's just going to spit out random digits at me. How can I turn these random digits that it's giving me into pretend coin flips?
Oh, okay. Are we still doing the one where it's like how often will heads show up and an even number shows up? Are we still doing that?
That was just an example.
Oh,
we don't
okay.
have to do that. Okay.
I thought that's what we were.
Okay. Yeah, we're just pretending. We're just trying to make pretend coin flips using random digits. The computer's just giving me random digits, and somehow I have to pretend that coin flips are happening. Yes.
I'm just so confused about the random digits. So you're saying assign to head, and then 0, 1, 2, 3, 4. What? Why are you saying you're assigning? It's just random. You're just flipping it. I just didn't understand the number.
You could just as easily assign even numbers for heads.
Oh, okay. All right. Have you ever been to a casino in California?
No.
No. Okay, not in California. Okay. So in California, You are not allowed, You are not allowed to play any games of chance other than card games. Okay, they've got this rule, right? So like if you want to play the game of craps, which use dice, like you go to Vegas, you throw the dice, and it's fun. The whole table cheers. Okay. You go to California, and then they're like, "Oh, you want to play California craps? Here's some cards." And you're like, "What the hell is this?" But what they're trying to do is they're trying to simulate the experience of craps using cards. Okay. Does that make sense? And so what they do is they have a deck of cards that have 1 through 6 and another deck of cards that have 1 through 6, and you basically pick out a card from this deck and a card from this deck, and these are your numbers that represent what happens when you roll the dice.
So why is it random if it's like assigned?
Oh no, so okay, so basically, and so that's what they're trying to do here. Okay, we're doing something similar, but not with cards. We've got a computer that's going to give us digits, and the numbers are random. The numbers 0 through 9, they show up in a random order. They show up in different orders. Sometimes they show up, you get sequences of 3s or whatever. You have no idea what number is going to appear next, okay? But overall, we know that each of the digits, 0 through 9, show up an equal number of times, okay? Or approximately in the long run. And so here, in order to simulate a coin flip where heads shows up just about as often as tails, okay, I have several options, okay? One of the options is I'm going to assign half of those random digits to heads and half of them to tails. Okay, does that make sense?
Yeah.
All right. Okay. All right, I mean, alternatively, I could have assigned the even numbers to heads and the odd ones to tails, or just as long as half are assigned to heads, or I've got an equal number assigned to heads and an equal number assigned to tails, we're okay. All right, what if I wanted to simulate rolling a die? Okay, so in real life, the faces 1 through 6 show up with equal probability. Alright. So I want to somehow show that the numbers 1 through 6 will show up equally. And but how can I do it with random digits? Okay, I'm sorry. Did someone say something about how to do this? Or was there a question? Or I don't know. Okay, yes. Okay, yeah, okay, so what do you want to do?
1 to 1.
Okay, so if you show if a 1 appears, that means you rolled a 1. And if a 2 appears, you got a 2, and so on all the way up to 3, 4, 5, and 6. That means you rolled a 6. Okay. All right, but what happens to digits 0, 7, 8, and 9?
Not on a die.
Huh?
They're not on a die.
They're not on a die, but they're going to appear. Okay, the computer is going to give these to you because it's a computer. It doesn't know you're trying to do a die roll.
Why do you need those numbers, those extra numbers? Don't you need just one?
No, yeah, I mean, okay. But all right, so it's not that I'm needing. I'm not telling the computer I need all 10 digits. It's just going to give me 10 digits. It has no choice but to give me all 10 digits. So what do I do when I see 0, 7, 8, 9?
Disregard it?
Disregard it. I'm just going to say, all right, computer, we're going to pretend that these things, they just don't exist. We're just going to ignore or disregard anytime those numbers appear. Okay? And so we're throwing away, you know, about 40% of the numbers that the computer gives me, but that's okay
It doesn't affect.
because what we're trying to simulate is rolling a die. Okay?
This
Yes.
is only for stuff like rolling dice and things that don't have 10 numbers, correct?
I'm sorry.
This only applies to things that don't have 10 numbers. Like rolling a die, it has 6.
Yeah.
So you.
So yeah. So we
No, I'm just
ignore.
double checking with you. That's.
Yeah. Okay. Yeah. So in this case, we want to simulate 6 possible outcomes.
Yeah. So those.
So
are
we're
just-
ignoring 4 of the other ones. Okay. Alright, is this working okay? Alright, what if I have, let's say there's 63 of you in my class, okay, not today, but okay, so 63 students in the class. Okay, and let's say I said, you know what, I hate teaching now, I'm going to just, I'm just going to give grades at random, okay, and I'm going to just say 12 lucky students are going to get an A+, and I'm just going to pick, out of 63 students, I'm just going to pick 12 of them, and I'm just going to give them A+, whether they deserve it or not. How can I do this so that it can be done, fairly, where everybody has an equal chance of being showing up? Okay, so what if I want to do this in real life? What's a way I can do this?
Names in a bag.
Okay, names. I put everybody's name on a piece of paper. I throw it in a hat. I mix up the hat.
Pick out random.
I draw out 12 names. Okay. Or yeah. Okay. So in real life, basically, I just want to make sure each student has an equal chance of being selected. Okay, 63 students in the class. Let's say pick 12 students at random. Alright, so how do we do this with the random digits? Okay, and so so just as an example of what random digits look like, and it's just a computer that's just spitting out numbers at you, okay? Let's just say the numbers that it spits out are 3, 4, 6, 8, 5. 4, 6, 7, 7, 5, 3, 2, 1, 3, 9. Okay, so this is actually on page A1 in your textbook, and this happens to be row 09 on page A1. If you want to know where these digits came from.
What?
Row 9 on page A1, okay? And so this is just the results of a computer spitting out random digits at you.
Is there supposed to be 15 numbers?
Yeah, I mean, I only wrote 15. I mean, there's hundreds on the page, but I don't.
I thought there were like 12.
Yeah, there's only 12 students, okay? So I'm not using, I mean, well, I'm going to use these, okay, numbers, but how can I use these numbers to pick 12 students at random? Okay, let's think about this. I've got 63 students.
You could choose 9 digits and assign 7 students per digit.
Or you could assign all males an even number, all females an odd number.
Okay. And then, all right.
Or you could assign, you can count over in rows, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay, so I think you guys are making this too complicated, and you are also limiting yourself in the structure of what can happen. Okay, so let me just open your mind here. All right. Okay, the computer doesn't care what I do with these numbers. It's just giving me numbers. 3, 4, 6, 8, 5, 4, 6, 7, 7, 5. Okay, it's just giving me numbers. So what I'm going to do is I'm going to create a list of all of my students. Okay, and I'm going to give each of my students a number. Okay, so I've got okay, so let's just say we've got Adam and Bob and Carol and whatever. Okay, these are the students' names. I've got 63 of them. Okay, and I'm going to all assign them an ID number. Okay, And I can start at 0, 1, but just, well, here. Yeah, I'm gonna just start at 0, 0, but I could have equally started at 0, 1, okay? And it doesn't matter, and I'm gonna just keep going. And then so the last student, what's the last student's number gonna be?
63.
Not 63, but 62, okay? Because I have 6, 0, 0 here, okay? So I got all the way up to student ID 61 and 62, okay? So these are the students. And when the computer gives me numbers, I'm going to say, okay, I'm going to take 2 of those numbers and say, oh, you gave me a 3 and then you gave me a 4. I'm going to say that's 34, and I'm going to pick student 34. Alright. Okay, what are the next, who's the next student I'm going to pick?
46 or 68.
Okay, well let's just not throw away all of our numbers, okay? I mean, so the next one that I get is 68, okay?
So we disregard.
We disregard it. There's no student 68. So I'm just going to say, okay, computer, that was no good. So ignore, okay, ignore 68. Okay, who's the next student I get?
54.
Student 54 gets selected. And then what?
Disregard.
So I ignore 67, I ignore 75, and then I pick student 32. What if, let me just manipulate, so let's just say this computer spit that out. What do I do now?
Disregard the next one.
Okay, so I would normally pick student 34, but student 34 has already been picked. So I have to ignore it because I can't repeat student 34. So ignore 34 because it's a repeat. Okay, and then maybe,
So no double dipping.
yeah, right. And then so the next student would be student 20 and so on and so forth. Okay. And so we can use any kind of random situation that we have in real life, we can simulate with random digits. Okay. Is this okay? All right. What about, let's say we wanted to play Monopoly and you lost the dice, but you happen to have a computer random digit generator. So in Monopoly, you roll two dice. And you add the 2 dice up, okay? And you move the total that appears. Okay, how can we simulate this with a computer or random digits? So let me propose a method, and you tell me if this is going to work or if this is not going to work. Okay? So I say you can show. That means when you add 2 dice together, you can get any 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. Okay? And so I'm just going to do the same thing that I did for the students. And basically, if I get 0, 2 through 12, I use that. And then I ignore 0, 0, 0, 1, and 13 through 99. Okay? I mean, we're ignoring a lot of digits, but that's not a problem. Is this going to work?
Yeah.
Yes or no? Okay, who thinks?
Can you repeat that?
So with this method, for 0, 2 through 12, would this work for simulating die rolls in Monopoly?
Yeah.
Okay, so who says Who says no? Okay. Why do you say no? I mean, similar, okay? So the students, I'm basically picking two numbers, okay? So I'm going to say, I'm going to just take 2 digits at a time, and if I get digits 0, 2, 0, 3, 0, 4, or all the way up to 12, I'm going to use that as my die roll, and if I get any other digit, 13 through 99, or 0, 0, and 0, 1, I'm going to ignore it. Okay? Will that work for Monopoly? Obey.
I would rather use 0 to 9 and ignore 0, 7, 8, 9.
Okay. But that's only one die roll.
You can't get a 0.
But then you can count it twice.
Okay, alright, okay, yes. So the truth is obey is right, and is it obey or obey? Obey, okay, obey is right. That's how we have to do it. We have to use 1 digit at a time to simulate one die, and 1 digit at a time to simulate the other die. We cannot use the 0, 2 through 12. But why not? Why not? Yeah, obey.
It's not convenient. Too many numbers to ignore.
No, that's not the problem, okay? The convenience is not the problem. I mean, because the computer, it's just giving us numbers, and it can do it very rapidly, and it doesn't matter that we're throwing away a whole bunch of the dice, okay? That doesn't matter. Yeah.
Is it because you can't use one number and then use 2 numbers? You
No,
have to either use-
that's also not the problem. Okay, yeah.
Because several numbers can add up to anything between
Okay.
12.
Yes. So what's going on is if you play Monopoly or any kind of dice game, which number shows up the most often? They're all equal? No, they're not. Okay. Otherwise we go to Las Vegas and we'd always be betting on the number 12, right?
I figure it depends on how somebody rolls it. That's also it.
Okay, so think of how many ways can you get the number 2 when you roll a die?
One.
There's only one way. You have to get 1 and 1. That's the only way to get a number 2. How many ways can you get a 3? You can get 1, 2, or 2 and 1. Okay, and those are different. Those are different. If you imagine one die is red and one die is blue, 1, 2 is different from 2, 1. Okay? How many ways to get a 7? There's 6. 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. Okay? There's 6 ways to get the 7. How many ways to get the 12? Only one. You have to get a 6 on the red die, and you have to get a 6 on the blue die. Okay? So 7 shows up way more often than 12. It shows up 6 times more often than the number 12 does. Okay? And that's why when you play the game craps, you lose when, well, they have it all set up, but basically you're trying to see your number before the 7 shows up, and so it's a tricky game. Okay? Well, not tricky, but if we did this method, the number 0, 2 will show up just as often as 0, 7. Okay, this is the rules of random digits. Each digit combination shows up equally likely just as often as any other digit combination. So this does not simulate this, okay? Because this is what's happening in real life. In real life, the numbers 1 through 6 on each die show up an equal number of times, but you're much more likely to get a 7 than you are a 2. Okay? And so over here, if we did this with the random digits, this does not work. All right? So what we must do is we must simulate, just like in real life, showing that we do die 1, and we do 1 through 6, ignore 0, 7, 8, 9, and then die 2, same thing, 1 through 6, ignore 0, 7, 8, 9, and then we take each of the results here and we combine them. Okay, I don't want to belabor this anymore. So the random digits, they're a tool that we can use to simulate kind of these real life scenarios, real life random events. All right. And so why would we want to do this?
For the probability.
Okay, so let's say, for whatever reason, the math behind calculating, if I ask what is the probability of rolling a 7? Okay? We're going to learn the math rules to answer this question. But let's say this method, let's say the math rules were too complicated for us to do it the analytic way. Okay? So we wanted to answer this. We're going to try to estimate this answer using simulation. Okay. Or actually, let's say you didn't understand coin flips, okay? And I asked you what's the probability that a coin lands heads? Okay. This will be actually an easier simulation for us to do. Okay. So I say, so here's a simpler. What is the probability of a coin landing heads? Okay. And we know that the answer is 0.5. Okay. So we know 0.5. Okay. But let's say we didn't understand this. Okay. We didn't know this. We can simulate or estimate this answer with a simulation, or estimate it with a real life experiment. Okay. And I just flip the coin. Okay. I take a coin and I flip it. And if I flip it 10 times, let's say the coin lands heads 6 times. What is my estimate for the probability of landing heads after 10 coin flips? So I can flip it 10 times. It lands heads 6 times. So at this point in my experiment, my estimate for the probability of landing heads is 6 out of 10, or 60%. Because I did it 10 times, it happened 6 times, so that's my best guess right now. It's going to happen 6 out of 10 times right now. Okay? I flip it 100 times. And let's say it lands heads 45 times. What's my estimate?
45%.
Yeah, 45 out of 100. Okay, so we can see our estimates aren't perfect, but they get us in the ballpark. Okay? And I can do, so what do I need to do to get an accurate estimate?
You're never really gonna get an accurate estimate.
Yeah.
Count the sides or count the possibility.
Okay, well, So that's going into the understanding of the actual point itself, okay? But using with a simulation or real life experiment, I just have to repeat the experiment many, many times and just count how often it lands heads, okay? Which is how we try to get like, what's the probability, what's the prevalence of, some disease out there, okay? We don't fully understand how disease spreads and every interaction and things like that, but we can come up with some estimate for, what's the prevalence of a certain disease just by, we survey different people and we say, okay, we surveyed 1,000 people and 20 people had this disease, so our current estimate is 20 out of 1,000. That's all they're doing, okay? Who's going to vote for, this candidate, okay? We don't understand what happens in a person's brain and why they're picking a certain candidate and things like that. But we ask 1,000 people, 520 say I'm going to vote for this person, so our estimate is 520 out of 1,000, or 52%. Okay, that's all we're doing here. So just the more things we do, our estimate gets better. Okay, and it might not ever be perfectly 0.5000, like 50% exactly, but it'll get pretty close. Okay, so if we want to do the same thing with rolling a 7, okay, and let's say we didn't have access to dice to roll and do this physical experiment, we could use the computer and we just say, okay, we're going to pretend to simulate 1,000 rolls of the dice. And then what do? What's the next step after simulating 1,000 rolls of the dice?
Divided by 2.
Divide by what?
By 2 because it's 2 dice.
Not 2 dice. What do I have to do? I have to count what?
How many sevens?
How many 7s I got? Okay. Sevens are recorded. Okay. And then what do?
Divide that number by 1,000.
I divide that by 1,000. Okay, so my probability, this is my estimated probability, is the count divided by number of simulated trials. Okay, and that's all we do. And sometimes this method of simulation is easier than trying to do the actual math of understanding this, okay? And we'll learn some of the math for simple problems, but this is one way to do it. Okay? So that's a tool that we have to help us understand random events. Anytime we look at this estimated probability, the term we use is sometimes the empirical probability. Okay? And this is based on like an actual simulation or real life something, okay? This is based on simulation or data rather than the mathematical analysis. That's the empirical probability. Okay, so if I see, so let's say I count 171, then my estimated probability is equal to 171 divided by 1,000. That's that, okay? So is the true number, true probability 0.171? Probably not, okay? Actually, no. But it's going to be close to this, okay? Or we expect it to be close to this, yeah.
Is there a number of trials that you should do in general, or is it very?
So the answer to that is do as many as you can, okay? Do as many as you can. And with a computer, we can easily ask the computer to do 10,000 or 100,000 trials. That's not hard, okay? If I were to tell you your homework is to flip a coin 10,000 times and count how many times it got heads, we would not want to do that, okay? Actually, they made prisoners do that back in the day because they wanted to understand probability and coin flips. And they had prisoners flip coins all day and count how often it landed heads and things like that.
And then they became Wall Street.
What's that?
And then they became Wall Street analysts.
Yes, but you guys are not my prisoners. I cannot have you do that, and that would not be the best use of your time. Okay. So, but this is a good way, and the computer doesn't have feelings yet, so we just have it do our prisoner work. So.
Luckily, it's not HAL.
Okay. Okay. So on the other hand, this is one way to find empirical probabilities. Okay, and the other way to learn probabilities is the theoretical probabilities using basically the rules or what we call axioms. Okay. And we find this with not from simulations, but with mathematical rules. Okay, and these are known as axioms. Okay, but whatever. So, for simple outcomes, these are outcomes that are equally likely as every other outcome, okay? So, each possible outcome is equally likely. So this is a single coin flip. Heads is as equally likely as tails. Okay. Well, the way we find this probability is equal to the number of outcomes or that satisfy the event divided by total number of possible outcomes. So in this case, for probability of getting heads, okay, well there's two sides to the coin. Okay, you've got the person and the shield on the back now, okay? Heads and tails. So there's two possible outcomes. How many of those outcomes satisfy the event heads? One. And then how many total possible outcomes? Two. So the probability of heads is 1/2. Easy. Okay? What about, let's think of a deck of cards. Okay? What if I ask, what's the probability of selecting spade? A card with a spade.
13 to 140.
Okay? Well, how many outcomes satisfy drawing a spade? 13. There's 13 cards, that's our spades. How many cards in the deck total? 52, which simplifies to 1 out of 4. Okay, and so that's the probability of drawing a spade. Okay, what about probability of drawing a red face card?
6 out of 52.
Okay. Yeah, so let's say there's going to be Jack, Queen, and King. Those are the cards that are face cards. Do you count an ace as a face card? I do not, because there's no face on that card. But some people say it's a face card. It's just a high value card generally. There's no face. Okay. Jack, Queen, King.
12.
And there's hearts, and then Jack, Queen, King of diamonds. Okay, those are the red face cards. So we have 6 out of 52 cards possible. So this is how we find the probabilities of simple outcomes or combinations of simple outcomes, because each card equally likely. Okay. One of the rules is known as the complement. Okay. The complement is spelled with an E, not an I, so it's not a nice thing that you say about probability, but it comes from the idea of completing something. Okay. So there's this movie, Jerry Maguire. Now it's like 14 years old now, but whatever. Okay. And the famous line is, "You complete me." Okay. The complement. It completes the possibilities. Okay. All right. The complement is the event that an event does not happen. Okay. So the complement of an event is basically when the event doesn't happen. Okay, so the complement, what is the complement of getting heads? Okay. The complement of getting heads is not getting heads. Okay? And we have a name for that, and that's called tails. But you have to remember that it's not whatever this is. Okay? So the complement of drawing a spade from a deck of cards. Not drawing a spade. Exactly. Okay. Now this seems very basic, but people will mess this up. Okay. And how do we find the probability of something not happening? Yeah.
Subtract the probability of it happening from the total outcome.
Okay. Yeah. Or we can just subtract it from 1. Okay? Because basically we just do 52 over 52 is 1, or 2 out of 2 is 1. So we just do, so the probability of the complement is equal to 1 minus the probability of the event. Okay? So if the probability of getting heads is 1/2, probability of not heads is 1 minus 1/2, which is 1/2. And the probability of getting spades 1 out of 4, the probability of not getting spades is what? 1 minus 1/4, 3/4. Okay? And these can also be represented in decimal form. 0.25, 0.75. Is that alright? Easy enough, right? Okay, so what's the probability of not getting a red face card? 46/52, yeah. 1 minus 6/52. Okay. Alright, I should note that the probability of any event is always going to be between less than or equal to 1, but bigger or greater than or equal to 0, okay? And that's the rule. So if you ever get the probability is bigger than 1, you did something wrong. If you ever get the probability is less than 0, you did something wrong, okay? You cannot have a probability greater than 1 or less than 0. So no event probability greater than or equal to 1 or less than 0.
Wait.
Yeah.
It can be equal to 1.
It can be equal to 1. I'm sorry. Greater than 1. Okay. What does it mean to have probability equal to 1? Okay, 100%. What does that mean? What does it mean to have probability equal to 100%? Huh? It happens every single time. It happens every single time. Okay? So what's an event that happens every single time?
Gravity.
Coin lands on something.
Yeah. Well, the probability that the coin lands on heads or tails. Okay? So what is the probability that the coin lands heads or tails? Okay? Well, that's always going to happen. Always going to happen. Okay? Unless you count the chance that a bird swoops out of the sky and eats the coin before it lands. So we're going to say it's negligible, so always going to happen. Alright, so there are a few examples in the book talking about looking at 2 different dice and why that one you need, you have to look at all of these things. Okay. Alright, let's think of, let me make up a table here. Okay, so this is called a contingency table or a two-way table, remember this? Okay, so let's say we have men and we have women. And let's say we also have, and then between the men and the women, we have between 18 to 25, or 18 to 24, 25 to 39, and then 40 and up. Okay, so let's just say these are the age categories that we've split up a group into. Alright, and okay, so let's say I've got 25 and 30 and 10 and 15. So what do I have here? I've got 40, 48, 53. Does that add up correct? Okay. Alright, so what if I asked, what is the probability? Okay, I'm going to randomly select one person out of the 93 people listed. Okay, what is the probability that this person I select at random is a man? Okay, so randomly select one person. Okay, probability that this person's a man?
40.
40 divided by 93, not 40, okay? Because 40 is a number bigger than 1. Okay, but 40 divided by 93 will give me a decimal, which is between 0 and 1.
0.4.
What's that?
0.43.
0.43?
Well,
Alright.
I think it's 0 and 1.
Okay, 0.43, great. Okay, what's the probability that the person is 40 plus? 10 divided by 93, so 0.11-ish.
0.12 or 0.11, I'm sorry.
Yeah.
1, 1.
1, okay, we'll go 108. Alright, okay, so this is okay? Alright. What if I said, what is the probability that someone is 18 to 14, or I'm sorry, 18 to 24, or 40 plus?
Add those numbers together and divide by 93.
So 18 to 24 in the 18 to 24 group or in the 40 plus group?
28?
So it's gonna be 65 divided by 93.
No.
Yeah, so the answer, we're going to do 55 over 93 plus 10 over 93. Okay, so we get 65 over 93. .70. Is this okay? All right. What about probability of man or woman? The person you draw is a man or a woman?
100%.
100% or 1, okay? So actually it's going to be technical, I'm going to do 40 over 93 plus 53 over 93, which equals 93 over 93 equals 1. So the probability that you're going to select a man or woman out of these 93 people is 1. So it's always going to happen that a person is a man or a woman. So far so good? What's the probability that a person I select is a man, or that the person is 40 plus?
It's 40 plus 5 over 93.
So our answer in the end is gonna be 45 over 93, okay? Now, because if we look at this, yeah, we've got this satisfies, and this satisfies, and this satisfies the OR condition, right? So the people in that group are men, these are also men, these are also men, and these people aren't men, but they're over 40, okay? So if we ask, what's the probability that someone is a man